Hello, TABConf. This man needs no introduction. Thank you.
Well, actually, my first slide, little introduction. So, yeah, I'm Travis. I've been working on Bitcoin for a while. Lightning Network, secure law contracts, interactivity, some of these things are on the wall. I was at MIT, and now I'm at Lightspark, which is cool, and there's some other Lightspark folks here for the first time, so that's great. Just want to give a shout out. Alvin is talking about UTXO tomorrow at 2:30, so let's see him. But today I'm going to talk about interactivity. I have a quick table of contents. So this sort of gives you an idea. It's a little bit rambly, but I think it's sort of an interesting thing that I and many others have started to deal with. And then I guess I unfortunately only saw a little at the end of Z-Man's talk just now, but people were like, oh, this is sort of about the same things with interactivity and how it makes things hard. I'm going to talk about that, and hopefully there's some fun moments here. Okay, so my general thesis now that I'm trying to get, I want to communicate it to people who are getting into this space and starting to build stuff and starting to make new protocols and make new ideas, as sort of this is sort of a warning, or this is from working on Lightning and DLC and UTXO and all these Bitcoin things. It's keep mispricing interactivity. We all sort of know, yeah, non-interactive is better than interactive, and you want to, round, Frost is round optimized, so it's hey, fewer rounds of interactivity, and these things are good. But it seems no matter how much we say, yes, interactivity is costly, we're still underpricing it. But yeah, then we have to ask, okay, what is interactivity, and how do these things work? So, one sort of aside, it's kind of funny, initially when I put this on GitHub, I was this will be an interactive workshop, where people will bring laptops and we'll connect to each other, and we'll do interactive things with computers. And I thought one example of how hard interactivity is let's say you have a laptop, and the person next to you has a laptop, and you want to transfer them a file. It's a megabyte. How do you do it? And it's without going through the cloud, right? And it's just kind of impossible. Yeah, you can do it, but it's really hard. And so ad hoc Wi-Fi, or if you connect to this Wi-Fi, can you find each other's IP address, and will it even route and stuff like that? So anyway, this was going to be an interactive workshop, and they're yeah, it's a talk. And so I will talk, and you can listen, or you can look at your computer, and you can eat a sandwich, and you can message people. So in that way, non-interactive is actually a lot more flexible, easier, and kind of free, right? You don't have to pay attention to me, and you don't have to do anything. And also they will record, yeah, it's a camera. They're going to record this, and the recording will be almost as good, not quite. You don't have the physical presence or whatever, and it's sort of, but the recording's going to be better because of this. So there are a lot of benefits to non-interactive. Oh, and by the way, if you want to make it interactive and raise your hand and ask a question, that's also totally fine. So the first cryptographic basics of interactivity, I want to explain this fiat-Shamir transform, which is, if it worked everywhere, it'd be amazing. It only works in certain specific cases. But when this was first sort of written about and discovered, it's really powerful because it takes a interactive protocol and just using a hash function makes it into a non-interactive protocol. And so, at least in all the examples, so I don't know, this was 86 or 88. I mean, this is pretty old as cryptography goes. And so I don't know if it was actually written in terms of the Schnorr identification protocol, but every example you'll find online is mostly talking about how there was a Schnorr identification protocol, and then applying the fiat-Shamir transform turns it into a Schnorr signature protocol. Disconnected. I'm non-interactive. So this may be familiar to people who are familiar with Schnorr signatures, but it's a little weird. It's a little different. So if you've looked at Schnorr signatures, I'm going to use capital letters as points on a curve, and little lowercase letters as scalars, and G is the generator point that everyone sort of agrees on beforehand. $sign means random number. So the initial Schnorr identification protocol was a way to prove that you know a private key or a public key without revealing that private key. And so your first setup is you have your public key A, right? You just come up with a random number, little a, multiply to the generator point, and that's your public key. That's the same as always. And then you make a nonce, K, they usually call it, and you transform that nonce K into R by multiplying and also by the generator. And this is like a one-time use thing. So when you want to prove to someone that you know the private key for A, you send R over. They send you a random number E back, and then you send them K plus A times E. Your private key times the random number they give you, plus the one-time nonce scalar that you used. And they can verify this. Then they can verify this by multiplying both sides by G and see that it all works out, right? So if you multiply this side by G, you get X times G. The receiver, the verifier can do that. And then on this side, they can do R plus your public key times E is what number they do. So this is useful, and this could be very useful for something like SSH, or something you're like logging into a server, and you interactively, they say like, hey, here's this random number as a challenge, and stuff like that. But much more powerful is the Schnorr signature, which just says, hey, instead of using a random number that the verifier provides to you, make up your own random number. And make it up in a way that's like hard to fake, hard to fake or whatever, by hashing your message and your notes. And this is just the Schnorr signature as used in Taproot all over the place. So this is like, seems kind of simple, right? It's like, hey, instead of sending something over, you're pre-committing to R, and then E is this random number they make up, and they send it back. Now there's like one shot. You just sign a message, send S to R, send S and R together, and that's your signature. And you can also, the bonus is you throw in this M, this message. It doesn't have to be there, right? You could omit M and have a sort of a Schnorr signature that this doesn't actually sign a message, but just proves that you know your private key. But throwing the message in there is even better. Now you sign a message, everyone can verify it. It's like super powerful. And the Schnorr identification protocol, like nobody uses it. It's like okay. Because also it's like, well, at this point, why not just do it in email and you're verifying both sides, blah, blah, blah. So this is like really cool. It doesn't work in a lot of places, right? There's, the general, if you have an interactive protocol that you're starting to work with, and the only thing you're needing from one side is randomness, then this should be like, hey, can I apply the engineer to this? Can I reduce the interactivity? But there's lots of cases where it's, well, the parties aren't just supplying randomness to each other, they're supplying signatures or keys or something like that. So I'll talk about Lightning and signatures. And I know there's lots of workshops about this kind of stuff, so it may be redundant, but there's 2-of-2 multisig, which is what we're using now, right? And you basically, in the opcode, you say, okay, object multisig, put a number 2, put the 2 keys, key A and key B, and put another number 2. And then in the witness script, when you're actually signing, you put a 0 and then a signature A, signature B. The 0, as far as I can tell, is a bug that Satoshi put in, we just are stuck with. But you have to put something there. So this is sort of simple, right? It's like, yeah, you say I want a signature for these 2 keys, key A, key B, and then I provide 2 signatures. With MuSig 2, what we're going to next, that's enabled by the Taproot software from like almost 2 years ago, it's much simpler, right? It's like you put an op1 to sort of indicate that it's segment B1. You put your key, and then the witness is just a signature. So it doesn't look like it's a 2-of-2 multisig. And no one can tell that it's 2-of-2 multisig, but it is. The way we got there is MuSig 2 is interactive, right? So there's multiple rounds of prompts and responses between the peers. So I think it's 3 rounds now, where you sort of first you first give the hash of your R point, and everyone like verifies those, and then you give your R point, and then you give your partial signatures, and then aggregate. But the multisig that we have now is less interactive, and it's message order independent. So for example, if you're sending Sig A and Sig B, like Sig B can sign before Sig A or after, it doesn't really matter, you just sort of put them together at the end. That's not the case with MuSig 2. So it's still interactive though, and that's one of the things, like what does it mean to be less interactive? Like, it's easier to code. I'm sure if people here have been like working on L&D or watching sort of L&D for the last year, like they're like, okay, Taproot channels, and they're like, yeah, like I don't know, February or something, and then it's like, okay, it's September, and they're still like, yes, Taproot channels real soon, because it's really hard. There's just a lot of complex state machines to just for 2-of-2 multisig with MuSig 2. But even with the 2-of-2 multisig with the opcodes, it's still kind of interactive, right? You have to send these messages to each other, and that's also one of the complex parts about Lightning. Because there's no real, like, I I don't know outside of Lightning if I've ever done a multi-sig transaction in Bitcoin. Because I guess you can do it with like PSBTs, but how do you get the PSBTs around? How do you connect other people? It's kind of tricky, and there's no mempool for this kind of thing, right? You can't. So that was sort of what I was talking about. But maybe there can be a mempool for stuff like PSBTs, and that would still be interactive, but like easier. So this is like hard and costly, and hopefully it works. But things, like things like Frost and Roast, where it's like really powerful, it condenses lots of different signatures and like threshold signatures into one thing. It'll work, it'll be great, but it's going to be a lot of work to implement. Okay, so that was signatures. Another thing that seems to me to be primarily an interactivity thing is address reuse, right? And this is one of the few things that like Satoshi sort of says what you should do in Bitcoin.pdf. He's like, a new key pair should be used for each transaction to keep them from being linked to a common owner. And so like, everyone, Satoshi says, don't reuse addresses. And yet, 14 years in, there's enormous amounts of address reuse, right? You just see it, I don't know, just click through a block explorer, and it's just like hundreds and hundreds of, like a transaction with 100 inputs, and they're all spending UTXOs that have the same key. And you're like, right? And why? Why is this happening? I don't think people are actively trying to make Satoshi mad and like, make him stay away because he's so mad that everyone's abusing his wonderful inventions. I think it's just interactivity. Sending a new address requires humans to interact, and that's like the most costly thing there is, right? It doesn't seem like a big deal, but it's like, I have to click new address, I have to copy and paste that, I have to send that somewhere, someone else has to receive that and do something and put it in their computer or something. And it's like, I do it. I don't think I've ever reused an address because I'm like, a Bitcoin nerd and I'm like going to do everything Satoshi said. But yeah, skipping it and reusing an address thousands of times, it works, right? Like signatures work, it all works. And so people sort of ignore it because it's really costly. So that's why I think the idea behind BIP 352 and the implementation, I really like the implementation, is great. And to me, this is the best solution because basically you should read BIP 352 and look at silent payments. I think it's a little past the point of request for comments.
It's to the
Okay, cool. Most of the discussion was earlier this summer, I guess, but it's nothing set in stone yet. So if you want to read it and say, hey, what about this? But the idea behind silent payments is you get one address and you can reuse it as many times as you want, but the address that shows up on chain, the pub key that shows up on chain is different every time. And this is not a new idea. The idea's been around for at least 10 years. But people were always like, well, this is very costly. Because basically what you're doing is you're doing a Diffie Hellman for every transaction, or I think in BIP 352 they do it once per transaction. But still, it's potentially an enormous amount of computation compared to right now. So right now, if you want to see if you got Bitcoin, you say, okay, here's my list of addresses, which you just translate to pub keys or pub key hashes. And then you just look at every incoming transaction that gets confirmed, and you look at all the output scripts, and you're like, are any of these mine? And it's literally just are these two byte strings equal? Which is one of the easiest things for a computer to do, right? With BIP 352, now you have to do a Diffie Hellman. You look at the signing keys, take that public key, take your own public key, do a Diffie Hellman, which, you can do thousands of them a second on your CPU, but that's still, I'm guessing, 1 million to 1 billion times slower than the equality check. But you know what? It's totally worth it. Because to me, this reduces interactivity. People just post one address, and then they have all the privacy they want. And CPUs are pretty cheap, right? Even though it's 1 million or 1 billion times slower, in practice, it's going to add 10 minutes to IBD. Or if you're syncing your node, it's an extra minute of CPU time a day, probably not even, probably a couple seconds worth. So it's totally worth it. And I think this is a really great idea of what we should be looking at. Okay, so this is sort of given these different things, here's sort of a ranking I have of interactivity and how costly these things are. So the first is people talking to people is insanely costly and no one can do it. And if your protocol involves humans talking to other humans, it's just 2 is like people talk to computers. People can sometimes talk to, interactive computers. So like people play video games, like, interaction with a computer, like, okay. Computers talk to specific computers. This is possible, but a little tricky. This is sort of like, I kind of think of it as like proof of stakey kind of things, where it's like, okay, this computer has to talk to that computer. Like, they have to keep track. Or, Lightning Network. I need to talk to the node I have a connection with. That's the hard part of Lightning. And then 4 is like, computers talk to any computer. And this is sort of what we think of with like the mempool, or like blocks, or like mining, where, yeah, it's interactive. Yeah, like, it's not the mempool. Like, I'm sure lots of people will like say, well, it's not that mempool. Every computer has a different mempool, right? But actually, we just sort of think of it as the mempool, and it works. Because you just throw your transaction at any computer on the network, and it gets there. So this is actually not that costly for computers to sort of randomly connect to anywhere and send out a message. And then something like computers compute, right? This is very cheap. So this is something like the silent payments, BIP 352, and where it's like they don't have to talk to anyone. They just have to like churn away at a CPU. And I think this is like getting cheaper and cheaper because you have extra cores and stuff. And then 6, obviously, the cheapest is nobody does it. So, and then one thing, sort of an aside I want to look at is computers compute is basically what Bitcoin does to reduce interactivity. And so here's sort of the Galaxy Brain and TED Talk thought leadership part, where it's like, wait, Bitcoin itself is trading interactivity for computation, right? How does Bitcoin solve, people have said from the beginning, like, oh, Bitcoin solves the Byzantine generals problem. And like, it kind of does. And I want to do an aside. So there's a really fun paper, sort of a joke paper, but it's called The Saddest Moment by a guy named James Mickens, written in 2013. This is satirical, and I guess he's at Harvard. He writes about Byzantine fault tolerance and like those kind of papers. He wrote this for Usenix. He wrote this after Bitcoin, 2013, but Bitcoin hadn't really caught on in academia by that point. Like, I went to university to try to get a PhD, like, because I was interested in Bitcoin and didn't know anything about cryptography then. And it didn't work. I dropped out after a year because nobody wanted to touch it. And so I was like, okay, academics don't like Bitcoin, fine. And it still is like, getting there, but it's still, academia is somewhat resistant to it. So it's a really funny paper. I encourage you guys to read the whole thing, but this is a diagram from it where he's sort of talking about interactive Byzantine fault-tolerant protocols. And, there's sort of, it's making fun of diagrams in other actual papers where it's like request, reject request, don't be a jerk, send all possible messages, send all messages again. And like, this is the, mess that is non-Bitcoin, non-proof-of-work-based fault-tolerant protocols, where it's like really interactive, really complex, and like I read them, I've read Raft, I've read stuff, Paxo, I don't know how So, and then there's also a really fun part where he's giving an analogy, and he says, suppose that I'm at work and I want to go to lunch with some of my coworkers. Here's what the experience would look like if it was a Byzantine fault-tolerant protocol. It's like James says, I announced my desire to go to lunch. Ryan says, I verified that I heard you want to go to lunch. Rich, I also verified that I heard you want to go to lunch. Chris, you do not want to go to lunch. James says, oh no, let me tell you again that I want to go to lunch. Chris, you do not want to go to lunch. And then it goes from there. So I put the link to the paper in the GitHub issue for this talk. It's a really funny paper. Like, it's super niche, right? Because it's like, who works on like Byzantine fault-tolerant protocols, right? It's like, so totally nerd comedy. But I think a lot of people in this room would appreciate it. And so if you think about it, like, Bitcoin fixes this, right? Mining uses enormous amounts of CPU or ASICs, I guess. But there's very few messages. And headers are 80 bytes, and those 80 bytes mean a lot. So you can sort of think of an interactive version of Bitcoin, or Bitcoin's consensus, where instead of hashing a lot and then giving like one message, that the nodes could talk to each other a lot instead. And what if you didn't have these hash functions that have these nice random properties? And so you sort of give nonces to other nodes and say, hey, how about this number I made up? No. How about this number? And instead of like hashing a trillion times and then coming up with one number that starts with a lot of zeros, you just keep interacting. And you can sort of think that, like, yeah, if we didn't have SHA-256, if we didn't have hash functions, maybe this would be how Bitcoin would have to work. And so we're leveraging the hash functions, the properties of hash functions in Bitcoin to take away all the interactivity and reduce, and like, you can still see the you can still see the processors there, right? Proof of work. When you see the 70 0 bits in front, you're like, that took 2 to the 70 tries, right? But I don't have to do 2 to the 70 things, or I don't have to listen to 2 to the 70 things. So I sort of like, here's the thought leadery, whatever, kind of, whoa, yeah, sorry. It's kind of a Fiat-Shamir transform for consensus, right? So instead of communication and identity and state machines and rounds and elections and leaders, you just do the work and you prove it. And the proofs are really small. So I think, like, I don't know, this was like making this talk when I was like, okay, what all these problems with interactivity. This is sort of what I was thinking, like, yeah, this is the sort of Bitcoin ethos. And I was talking to Josie, who's sort of programming the 352's silent payment stuff for Bitcoin Core, and he was really into it. I'm like, dude, this is Bitcoin, right? You're getting rid of interactivity and just like throwing a bunch of CPU work at it. Yeah. Okay, so, and then I want to talk a bit about Lightning Network for a second. So Lightning Network is still too interactive. I think that's one of the issues we have to like try to fix about it. There's lots of messages and graph building and stuff for the computers. And people have to think about it a lot. Like, where do you peer? Like, who do you connect to? It's not like you just connect to the Lightning Network, right? Like, with Bitcoin, you sort of do. Like, yes, if you look and in the command line and you say, like, get peer info or whatever, it'll show, like, oh, you're connected to these 8 or 10 other nodes. But it's totally random, you don't care. Whereas in Lightning Network, like, you do have to care. So I think it's getting better, and we're sort of converging on sort of the right way to do things, and hopefully reducing settings and options. But we're still not really there. Like, Bitcoin has those options as well, so like you can say connect equals in your bitcoin.conf file, and you can connect to specific nodes if you want, and I've used that for like testing and like writing tests and stuff, but nobody really needs it. And so how do we make like a non-interactive Lightning Network, right? It seems crazy, it's like impossible, but maybe you can like feel non-interactive, right? So things that we think of are like, people say the mempool, right? And that's actually really good because it means that it's like achieved this level of abstraction where like it's just this weird blob that's called the mempool, and you just like throw transactions into it, and then it works and your transaction gets confirmed correctly. And same with the blockchain. Like, yes, everyone has a different blockchain on their computers, but the consensus like makes them all the same. So people say these terms like the mempool because that's how it feels. And also, like, I think it's really interesting looking at the terms Bitcoin has sort of started, where like I think in a few years like UTXOs will just mean money, and everyone will say like, and then the term I've heard a lot now is probably catching on is a spent UTXO. So that's the new concept. So yeah, hopefully we can get to something where it's like I put the money into the Lightning Network. And it's like, what? Like, and the like nerds among the real nerds will be like, no, that's not how it works. Every channel has a different this and every node. And it's like, right, but if people think of it that way, if they're getting to the point where they're just like, I don't know, I put the money in LN, now I can move it around, like that means we've like gotten it to a really good point. And so we're definitely getting there. There's a lot of work in like async receive, trampoline payments, to minimize like how much interactivity you need to have as a sender, some of the Volt 12 stuff. So I think one of the things is like we need to keep thinking of more ideas on how to make Lightning Network more non-interactive. And so the last part, there's some hand-wavy ideas. I want to sort of pitch DLS. I know it's like somewhat controversial. It's a signature algorithm from 15 plus years ago. And it does some weird, it has some very powerful non-interactive properties. So anyone can combine signatures after the fact. And even a miner, so you can say, even for different messages. So right now in a Bitcoin block, you have maybe 5,000 inputs with signing thousands of different messages, and from let's say 5,000 different pub keys. And a miner could say, construct a block, take all 5,000 of those keys, add them together, take all 5,000 messages being signed, add those together, and only give people the sums of those signatures and keys, and then every verifier, so everyone who got that block could verify that, like, yep, all those signatures work on all those messages. So that's like sort of the ultimate in non-interactive multisig, where you weren't trying to multisig. You were just signing your transaction, and your signature got smushed in with someone else's transactions and signatures. And so it doesn't necessarily, like that would obviously be a consensus change to like let miners do this. But it's still, even if it's not a consensus change, and you just say, look, we're going to allow BLS signatures, the trade-offs, of course, is more CPU, which is like, well, that seems like a good trade-off. And a little different in this case because with BLS, every verifying node has to do that extra CPU work. So that's not quite as good as like every participant has to do more CPU work, but and it's based on some. It's not just based on discrete log assumption. It's some of the curves that we're using are like a little different, and some people are sketched out by it. But I think it's like definitely something people should look at, like because there's a lot of interest in stuff like ARC and LN symmetry and all these different protocols, and it's like, hey, what if? And people are sort of like, okay, assuming you have OpCTV, we can do this. Assuming we have any pre-doc, we can do this. I don't think people are really looking at BLS, and it's like, hey, if we have BLS, what can you do? I think that it's just something to like throw out there. Like if people are looking at new protocols to reduce interactivity, this might be a really cool tool. Because if it's really powerful and we come up with something good, like hey, maybe we could software it. Who knows? It doesn't seem that much crazier than something like Ops. And then I guess unfortunately I didn't see Z-Man's talk just like half an hour ago. But I should have, or we should coordinate. We should interact. That's the problem. We're not interactive. But like some kind of mempool ++ where you're like, yeah, can we get some kind of mempool-like thing for not valid signatures that are not valid transactions that are immediately going to go into a block? And so obviously the big problem is denial of service, where someone just going to try to spam you. So I think this is maybe different from what you're saying, but I was sort of thinking. You can have some fixed amount of storage per UTXO, like use the UTXO set as your scarcity, because you can sort of say, well, I'm already storing this UTXO in my database. Well, if you do TreeXO, which we'll talk about tomorrow, but you can say, okay, well, I've already got like 70, 80 bytes, whatever in this database. I could potentially keep some extra data associated with each UTXO and allow people to prove they own it and like add a little bit of data that then I'll like gossip through the network. Make it so that you can't necessarily query, so they can't keep asking for the same things, but like, look, if you want this data, you're gonna have to get all of it, right? You don't get to specifically say, hey, what's the data associated with this UTXO? It's just, hey, dump the whole thing. And maybe something like that could help with coin join, multi-sig, DEXy kind of stuff, where you're like, I want to make a ordinal transfer or whatever. So, I don't know, those are two sort of ideas I have, and we should interact. I think that's it. Yeah, so thanks for coming. I guess I look forward to interacting with everyone, or not, we can just share our work.
Yeah.
Questions? Sure. Yeah, so here's the interactive part. Already, interactivity is hard.
Anybody has any questions?
Saddest moment when you can't be an introvert anymore.
Can you speak a little louder?
Yeah, sure. You said BLS is controversial. Can you elaborate?
Oh, okay, so BLS, I don't know if it's like controversial. Like, I've heard some people say they're not comfortable with it. So Schnorr signatures have a reduction to the discrete log problem. So like, you can say, if you can forge Schnorr signatures, you can break the discrete log problem, right? And that's what everything's hinging on. BLS is a much different, I think, I'm not an expert, but I think the way BLS originated was someone saw a weakness in certain types of elliptic curves. And the weakness is decisional Diffie-Hellman. Okay, so hopefully people sort of know what Diffie-Hellman is. It's like Alice has a key, Bob has a key, and they sort of combine them and then make a third key, and only they will know. And there's two properties of Diffie-Hellman. It's like computational Diffie-Hellman, so like only Alice and Bob can then make that third key C. And then there's decisional Diffie-Hellman, which is if I'm a third-party observer and I see Alice and Bob, and I know their keys, and then I'm given a third key, can I tell if it is the Diffie-Hellman point that they created or not? And for normal stuff, like in the curve we use, sec p, 2p, 6a1, neither is possible, right? If I don't know Alice's or Bob's private key, I can't compute this point. And even if I'm given a point, I have no idea if it is their Diffie-Hellman point or not. What BLS uses is a curve where computational is hard, so I can't, compute the Diffie-Hellman point unless I know a private key. But I can, if given a Diffie-Hellman point, check if it's valid or not, right? So if I'm given key C, I can say, yeah, that is the Diffie-Hellman point between A and B. Oh, interesting. And so when this was sort of found, it's like, hey, this is kind of a weakness in this curve type, because we sort of assumed you couldn't do this. And what BLS does is it leverages that property to make really powerful signatures, because basically what you're doing is your signature is the Diffie-Hellman point between your pub key and the message. So you turn the message you're signing into a pub key, and then do a Diffie-Hellman, and then everyone can verify it. And then it makes it like really powerful to like add keys, add messages, add them all up, and then you're done. And so this is part of the sort of unease where it's like, well, it was discovered as like a weakness, and then people like went with it. So I have heard some people being like, it's not, like, is it secure? And then other people are like, it's totally fine. Like, obviously, I've talked to Dan Baudet, and he's like, yeah, this is great, this totally works, but use the B in BLS, so it wasn't. Yeah, so that's part of that. Now we have amplified interactivity.
So Taproot has left the door open for upgrading the key and signature scheme without having to like upgrade the whole witness program. Could you use that to add BLS signatures into Taproot?
Yeah, so I mean, I guess, it would either be a new opcode. I don't know, at that point it'd probably be a new segment version, where you're just like, okay, segment V2.
New segment version.
Yeah, probably. I mean, yes, you can, like, there are
Because
openings.
that is already like kind of commits you to CCP256K1.
Yeah, you'd have to change the curve for something like BLS, so like, you couldn't use the same public keys. So you'd probably just have to make a new version of segment, so it'd be like segment V2 or something.
I don't know, maybe some kind of the sweet love equivalent.
Or you could use the Taproot commitment to commit to a BLS key.
Yeah, it's possible.
There's ways, but like,
It's
I don't know. That's like a big discussion question. I don't think you could. It wouldn't be like a clean like, oh, just use this new algorithm with the same puppies. You'd have to change quite a bit.
No more questions?
Okay, cool. I put some links in the little GitHub issue, so if you want to see the funny papers. So thanks, and yeah, go see all those cool talks. Thanks, everyone. Also, I feel after that sort of having a cold. I'm like better today, but I'm still nowhere.